Welcome to the first lesson for Chapter 2, where we'll be looking at the basics of quadratic functions. So what we're looking at today is completing the square, the quadratic formula, and the discriminant. So you'll notice that there isn't a study design dot point, and that is because these skills here are assumed. So we just assume that you learned them in units 1 and 2 or in year 10. So we're going through them in this lesson just to jog your memory. First up, we are looking at completing the square. So our key takeaway here, we use completing the square to transform a quadratic into turning point form. So from this polynomial form where you've got x squared plus bx plus c to the turning point form here where we've got y equals x take away h all squared and then plus k. So where our turning point is the coordinate hk. So the process for completing the square is if we've got y equals x squared plus bx plus c, what we're going to do first is halve what the b value is and then square it. So you'll see that we've got that there. So we're going to add that and then we're also going to take that away. So we're not actually changing the value of our quadratic, we're just changing what it looks like. So when we do that, we get b squared over 4 and then take away b squared over 4. And then putting that into the bracket, we're just going to use the b on 2 first and put that into a bracket and square it. So that's what this part here is doing. And then we need to take away the leftover part, so the negative b squared on 4, and then add our c at the end. So that's going to help us form our turning point form. If we have a quadratic where we've got a coefficient of x squared bigger than 1 or less than 1, so we've got an a value there, first we're going to take out a as a factor, and then we're just going to repeat the steps above here. All right, our first example, we are rewriting this polynomial here into turning point form by completing the square. Now again, the first step is to halve this b value here. So I'm just going to rewrite that. So we get y equals x squared plus 6x, and then we halve our 6 and then square it. And since we've added that, we're also going to take it away again so that we're not changing the value of anything. And then we've got our take away 5 at the end. So our next step is to simplify there. So we end up getting y equals x squared plus 6x. And then we've got 6 over 2, so 3. And then 3 squared gives us 9. So plus 9 and take 9. And then take away 5. So you'll see that the first 3 terms here, so the x squared plus 6x plus 9, that's going to form our perfect square. And then the negative 9 and negative 5 is going to be that y coordinate of the turning point. So from here, we're going to change it into a perfect square. Again, we're going to use this 6 over 2, so our 3, and put that into a bracket with x. So we'll get y equals x plus 3. We're going to square that, and then we've got the negative 9 take away 5 on the end. So we'll have negative 14. So that is our polynomial there in turning point form. Another example here, however, we've got a value for a that is not 1, so we've got 2x squared instead. So first thing we need to do is take that out as a factor. So I'm just going to rewrite that as y equals 2, and then in brackets, we've got x squared plus 16x on 2 plus 11 on 2. And I'm just going to simplify that because we know that 16 divided by 2 is 8. Okay, so for now, we're just going to ignore that 2 on the outside of the bracket and just deal with the inside of the bracket. So we have 8 here as our b value. So now we're going to halve that and square it. So we end up getting y equals 2 times, then in brackets, we've got x squared plus 8x plus 8 on 2 squared, which will become 16. Take away 8 on 2 squared, again, becomes 16, and then plus our 11 over 2. So what we need to do now is inside the bracket here, the first 3 terms there, they are going to form that complete square. So we're going to end up with y equals 2 out the front, and then x plus 4, again, because we used our 8 divided by 2 to form this value here. We are then going to square it. I'm going to have to use some bigger brackets though to make sure that I've got everything within the brackets there. And lastly, we've got the negative 16 plus 11 on 2. So in order to combine those, I'm just going to rewrite that as take away 32 on 2 and then plus 11 on 2, just to make it a little bit easier to add those together. So combining those 2 fractions there, we end up getting negative 21 on 2. And now we can multiply the 2 on the outside here by everything inside the brackets. So we'll end up getting y equals 2 outside the brackets, x plus 4 squared, and then these 2's can cancel out. So we'll get take away 21. Alrighty, next up we are looking at the quadratic formula. So if we cannot factorize easily, or if we can't complete the square, then we're going to use the quadratic formula. So this is used to find what our x-axis intercepts are as well. So on the right hand side, I've got a misconception there. So it is only to be used for quadratics. It's in the name. I see this happen a lot when students try to use this for a cubic function because they think they have values of a, b, and c. However, it's not going to work. It'll only work for quadratics. So please, please, please only use it for quadratics. Now, I've got a video coming up in a couple of lessons time to help you memorize the quadratic formula if you haven't already. So have a look out for that one. But for now, we're just going to look at what this is. So we've got x equals negative b plus minus the square root of b squared take away 4ac all over 2a. And what we can actually see is we've got this negative b on 2a is actually going to be our axis of symmetry. So that is the invisible line where the parabola can fold itself and be symmetrical. So we've got the plus minus because that's going to be our left and right axis intercepts. Okay, so our question here is solving the following for x. So we've got 2x squared plus 5x take away 1 equals 0. So this is the tip here that we are finding our x-axis intercepts. So firstly, we need to identify what a, b, and c are. So we've got a is 2, b is 5, and c is negative 1. So I'm just going to rewrite the quadratic formula up the top here. So we've got negative b plus minus square root of b squared minus 4ac over 2a. And then we're going to substitute in our values to find our x-axis intercepts. So we've got x equals negative b, so negative 5, plus minus the square root. So we've got b squared, so I've got 5 squared. Take 4ac, so 4 times a, which is 2, times c, which is negative 1, and all over 2a, so 2 times 2. So simplifying that, we get negative 5 plus minus the square root of 5 squared is going to be 25. And then negative 4 times 2 times negative 1 is going to be positive 8. And that's all divided by 4. From here, we're going to add the 25 and the 8. So we get x equals negative 5 plus minus square root of 33 all over 4. And we're just going to leave our answer in that form as well. We're not going to find decimals unless we have been told to. A little tip there. In your exams, you will need to leave your answers in exact form unless you have been told to change it to a decimal. So lastly, we are looking at the discriminant. So if we've got a polynomial here, y equals ax squared plus bx plus c, the discriminant here is given by b squared take away 4ac. So that actually is part of our quadratic formula. And what that is going to tell us is if any solutions exist for the x-axis intercept. We have 3 possible solutions. So if we've got our discriminant is greater than 0, then there are 2 x-axis intercepts. If our discriminant is less than 0, then there are no axis intercepts. The reason being because since this is part of our quadratic formula, our b squared minus 4ac, if this is less than 0, we can actually take the square root of a negative number. So therefore, we've got no x-axis intercepts there. If our discriminant equals 0, then there is exactly 1 intercept. So we've got a repeated factor there. Putting that into practice, we are going to see how many solutions there are for this equation here. So we've got negative 3x squared plus 5x plus 1. So again, our discriminant, we've got b squared minus 4ac. And then we're going to substitute in the values that we know. So we know that a is negative 3, b is 5, and c is 1. So putting that into our formula, we get 5 squared, take 4 times a, which is negative 3, and then times 1. So we get 25. Now we've got negative 4 times negative 3, so that's positive 12. So 25 plus 12. Straight away we can see that is positive, so we end up getting 37. So therefore, there are 2 solutions for this equation. So here is a summary page of everything we went through in this lesson. So we looked at completing the square, the quadratic formula, and the discriminant. What's coming up next is the key features of polynomials, so sketching, quadratics, cubics, and quartics. So we'll see you then. I hope you liked that video, and if you didn't, then please don't hate me. But it is a really good way to help you remember the quadratic formula. So what we'll be looking at today is the key features of polynomials. So in this lesson, we are looking at features of quadratics, cubics, and quartics. So recapping what you would have learnt last year, we're looking at quadratics first. So these are functions that can be written in 3 different forms. So the first one we've got here is the turning point form. So the values of h and k here actually tell you what the turning point is going to be. The next form we've got is the factorized form. So the values of E and F here actually tell you what your x-axis intercepts are going to be. And this A is just a dilation factor, so it's stretching the graph upwards and downwards. And the last is our polynomial form of a quadratic. So it's the normal form that you would normally see. So quadratics have 1, 2, or no x-axis intercepts, and they will always have one stationary point or a turning point. So looking at the graph over here, we have the graph of f of x equals x squared, so that is your standard parabola. For this one, the range is from 0 to infinity, and notice how infinity is not included there because we can't actually reach it, and our domain is all real numbers. So the next one we have is the graph of f of x equals negative x squared, and that is a reflection in the x-axis. We have a range here from negative infinity to 0, and again, noting that we don't include negative infinity, and the domain is all real numbers. For this example, we are finding the equation of a quadratic with a turning point at 2, 1, and also goes through the point 4, 2. So since we've been given the turning point, we can use our turning point formula. So the first step here is to substitute in these values, so 2, 1. So remembering that h is 2 and k is 1. So this gives y equals a, x take away 2 squared, and then plus 1. Okay, now we need to find what a equals. So we're going to use the point 4, 2 over here. So we have y equals 2, and then x is 4, and then we're going to solve for a. So solving for a gives a equals 1/4. So now we're going to substitute that back into the equation to find what our equation is going to be. And doing that gives y equals 1/4 times x take away 2 squared plus 1. Again, this is a recap of what you would have learnt last year in Unit 1 and 2. So we're looking at the features of a cubic function. So again, they can be written in 3 different ways. The first is the turning point form. So again, the values of h and k here are going to tell you a stationary point, but in this case, it's going to be an inflection point. The next form, we have the factorized form. So we're looking at the x-axis intercepts here. And noticing here that if we have a square there, that is actually going to be a repeated factor. So that is going to sit on top of or below the x-axis. It's not going to cut through. And the last one is the polynomial form of a cubic. So this is a standard form that you'll see. Okay, looking at this graph here, we have the graph of f of x equals x cubed. So that is our standard cubic. And we can see that it's starting in quadrant 3 and then finishing up in quadrant 1. So our range is all real numbers, and so is our domain. And we can see here that we have one stationary point, which is actually an inflection point. Next, we have the graph of f of x equals negative x take 2 squared, and then x plus 1. So since we have this square here, we're going to have a repeated root when x equals 2. So that is this point here. So again, you can see that it's just touching the x-axis, but not cutting through. And then we have x plus 1, so that means that we have an intercept when x equals negative 1. So that's this point over here. The negative in front of this graph here is a reflection in the x-axis as well. So we're starting in quadrant 2 and then finishing up in quadrant 4. To sketch the graph of the following cubic function, the first thing we're going to do is note the x-axis intercepts. So solving for x here, we get x equals 1 and x equals 2. Now we need to figure out what the y-axis intercept is going to be. So we're going to let x equal 0 and solve for y. So letting x equal 0, we end up getting y equals 2. So the next step you want to do is mark in your x-axis and your y-axis intercepts on your graph. When sketching the graph, make sure you note that we have a reflection in the x-axis. So we're actually going to start in quadrant 2 and finish up in quadrant 4. So letting your graph cut through the y-axis at 2 and then cutting through when x is 1. And then again, we have that repeated root at x is 2. So it's just going to touch the graph there and then go down. Lastly, we are looking at features of a quartic function. So the main thing you need to know is that quartics have a leading term with degree of 4. So that means that the highest index there is going to be 4 for our polynomial form. Quartics can have between 1 and 3 stationary points, and they can have between 0 and 4 x-axis intercepts. So kind of like a parabola, how we can have our graph above or below. So that's how we can have either none or many x-axis intercepts. Looking at this graph here, f of x equals x to the power of 4. Again, kind of looking like a parabola with a bit of a flatter bottom there. We can see the range is going from 0 to infinity, and our domain is all real numbers. So again, similar to a parabola or a quadratic, and we have one stationary point there. Another graph, we have f of x equals negative x take away 2 squared times x plus 1 squared. Now, what we learned before is that this square is a repeated root that is going to sit on the x-axis at those points, and the negative is a reflection in the x-axis. So it's kind of looking like an M here. If there wasn't a reflection there, it would look like a W. So our range is going from negative infinity to 0. Our domain is R, so all real numbers. You can see that we have 3 stationary points here. And again, those 2 repeated roots there at x is negative 1 and x equals 2. For our worked example, we are sketching the graph of this function here. So again, the first step you want to do is figure out your x-axis intercepts. Solving for x here, we get x equals negative 3, x equals 2, and x equals negative 1. So you can see that from the equation there. So we just basically take the opposite of what's here. And when x is negative 1, we have a repeated root as well. So now we need to solve for the y-axis intercept, so letting x equal 0. So solving for y, we get y equals negative 6. And let's just pretend that I made this graph really nice and extended it down to where I needed to. So just ignore my writing down there. So what we do now is we plot in our points and sketch our graph. So you can see here we have an intersection there when x is negative 3. We have the repeated root there when x is negative 1, our y-intercept at negative 6, and the other intersection there at x equals 2. In summary, if the highest degree of a polynomial is even, then the graph will turn back on itself. And what I mean by that is if we have our parabola here, it's starting up in the positive y-axis, and then it is finishing in the positive y-axis. So it's turning back on itself there. And the maximum number of x-axis intercepts is the highest degree of the polynomial. So if we have our polynomial y equals x to the power of 4, then that is the highest number of x-axis intercepts that we can have. And if the highest degree of a polynomial is odd, then the graph will go from positive to negative or negative to positive. So for example, for our cubic, our standard cubic starts in the negative y-axis and then finishes in the positive y-axis. And lastly, if a factor is squared, it is a repeated root. So when you are sketching the graph, it's only going to touch the x-axis, not intersect. And in the next lesson, we are looking at arithmetic of polynomials. So we'll see you then. Just a pre-warning for you, I'm going to be saying polynomials a lot this lesson. So not sorry. In this lesson, we are looking at arithmetic of polynomials. So we'll be looking at the language of polynomials, polynomial arithmetic, and equating coefficients. So what is a polynomial? So polynomials are functions that can be written using this form here, where the value of n, so our index here, belongs to the natural numbers. They are our counting numbers that include 0. The leading term of a polynomial is the term with the highest index, and the degree of a polynomial is the index of the leading term. So for example, if we have y equals x to the power of 4 plus x to the power of 3, the degree of the polynomial here is 4, and that's going to make it a quartic. Some examples of polynomials here, we have a polynomial where it equals 2. This is actually a polynomial, even though it is a constant. We have a linear here, and then we've got some literal equations there. For the polynomial p of x equals 2x cubed take away 3x squared plus 5x plus 7, we are finding p of negative 1. So we are substituting in x equals negative 1 to find what our function will equal. So firstly, substituting in x equals negative 1, that gives us 2 times negative 1, take away 3, take away 5 plus 7. Simplifying that, we get p of negative 1 equals negative 3. Our second example, we have p of 2, so substituting x equals 2. So substituting x equals 2 gives us p of 2 equals 21. Now this example here, we have an unknown value, so we are trying to find the value of a. We've been given that p of 1 equals 0. Firstly, we are going to substitute x equals 1 and let it equal 0, and that will help us find the value of a. In doing that, we get 1 plus a plus 2 take away 5 equals 0. Simplifying that gives a take away 2 equals 0, so therefore a equals 2. So we can add, subtract, multiply, and divide polynomials. What we're going to be doing now is just add, subtract, and multiply. We'll look at dividing them later. The sum, difference, and product of two polynomials is also a polynomial. So we have some properties here on the right-hand side. So to give you some context here, if we have f of x equals x plus 1 and g of x equals x squared, then adding those two together, we get f of x plus g of x, so pretty straightforward there. Next, if we are subtracting, we have f of x take away g of x. So again, we've got f of x there, take away g of x, again, pretty straightforward. And lastly, if we are multiplying them, we have f of x times g of x. So we've got f of x here times g of x. So now we have to expand and we get x cubed plus x squared. For these polynomials, we have f of x equals 2x take away 1 and g of x equals negative 2x cubed plus 3x. Firstly, we are finding g of x take away f of x. So when you are writing that out, just make sure that you put some brackets around f of x. Because we have a negative here, we don't want to get confused. Okay, so we end up getting negative 2x cubed plus 3x, take away 2x, and then plus 1. And simplifying gives negative 2x cubed plus x plus 1. For b, we are multiplying our two polynomials. So we have g of x times f of x. So in order to multiply g of x by f of x, we put the polynomials in brackets and then we are going to expand those. And expanding those brackets gives negative 4x to the power of 4 plus 2x cubed plus 6x squared plus 3x. Lastly, we are looking at equating coefficients. So this is actually going to help us with division that we'll look at later. So polynomials can also be expressed as the product of two or more factors. So as an example here, we have this polynomial and it can be written in the form of x take away 5 and then multiplying in brackets ax squared plus bx plus c. And then we've got r on the end. So we'll learn more about that in our next lesson. In order to equate the coefficients, firstly, we need to expand the brackets on the right-hand side. So we're looking at these brackets here. So they'll be on the right-hand side of your equation. Next, you're going to write a list of the coefficients of each of these terms and let them equal the coefficients of the terms in the original polynomial. And that process there is equating coefficients. So then you are going to solve for a, b, c, and r. So we're going to put that into practice. So we have this polynomial here, and it can be written in the form of x plus 3 times ax squared plus bx plus c, and then plus r. So we need to find the values of a, b, c, and r. So our first step is to expand this on the right here. So after we have expanded those brackets, the next thing we need to do is collect the like terms. And what I've done is I've taken out the common factor x squared and then x, so that I can equate the coefficients much easier. So our next step is to write down the list of the coefficients, starting with the highest term. So we have 2x to the power of 3. So our coefficient there is 2, and I'm going to let that equal the coefficient of the expanded terms on the right-hand side. So we have ax to the power of 3, so a is the coefficient there. Our next term for the polynomial is x squared, so the coefficient there is 1. And I will let that equal to 3a plus b. The next coefficient is negative 5. And we're going to let that equal 3b plus c. Lastly, we have our constant terms. So we have 2 equals 3c plus r. So we already have the value of a. So we're going to substitute that into our next equation. 1 equals 3a plus b. So we get 1 equals 6 plus b, meaning that b equals negative 5. We're then going to substitute that into the next equation. So we have negative 5 equals 3b plus c. So we get negative 5 equals negative 15 plus c, meaning that c equals 10. And lastly, substituting that into our constant term there. So 2 equals 3c plus r. We get 2 equals 30 plus r, meaning that r equals negative 28. So in summary, polynomials are functions that can be written using this form here, where the index there is a natural number, including 0. So our counting numbers, not negative numbers. And we can add, subtract, divide, and multiply polynomials. And the sum, difference, and product of these will be a polynomial. We can also equate coefficients to write them as a product of two factors. And we'll again use that a little bit more in our next lesson when we divide and factorize polynomials. So we'll see you then. Okay, this is a plea to all of you students out there. Please, 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 do not do this. Okay, this doesn't work. Every time you do this, you give your teacher 5 new grey hairs. She's only 31. In this lesson, we are looking at division and factorization of polynomials. So firstly, we'll start with division of polynomials, and then we'll look at factorization of polynomials. So the main purpose of dividing polynomials is to sketch higher order polynomials. We know we can easily sketch quadratics and cubics, but then when we get into quartics, it gets a little bit trickier. So we can use long division, synthetic division, and equating coefficients like we did in the last lesson. So what does this look like? So if we have polynomial f of x divided by g of x, we have this equation here. So we get g of x as the divisor and f of x as the dividend. We get q of x being the quotient, so what is left over, and then r of x is going to be the remainder. So if it doesn't divide evenly, we may have a remainder. This is generally a constant, but sometimes it's not. So for an example, numerically, that's what this looks like. So if f of x equals x cubed take away 7x take away 6, and g of x is x plus 1, then our first function, f of x, is our dividend. Our divisor is x plus 1, so what we are dividing by. And then our quotient, so what is left over, is x squared take away x take away 6. In this first example, we're going to use long division. We're going to write our divisor x take away 2 on the left-hand side, and then we're going to draw nearly a box on the right-hand side and put our dividend. So f of x equals x cubed take away 2x squared, take x plus 2. All right, our first step is to divide our first term x cubed by x. So in doing that, we get x squared. And I've written that above the term here, 2x squared, because they have the same index there. What we do then is we are going to multiply x take away 2 by x squared, and that's going to help us figure out what is left over. So x times x squared gives us x cubed, and then x squared times negative 2 gives us negative 2x squared, and we are going to take that away from our original polynomial. Just remember to keep these in brackets as well, because when you're dealing with negatives, we want you to make sure that you are taking them away properly. So once we've taken that away, we are left with negative x plus 2. So I've just brought those down to that next line. And then we repeat the process. So I'm going to divide negative x by x and write what's left over up the top there above the constant term. So I get negative 1 at the top there. And again, multiplying x take away 2 by negative 1. So that's going to give me negative x plus 2. Again, I'm going to take that away from negative x plus 2, and I get 0. So I have no remainders there. So we can write our answer like this. So we can have our dividend and our divisor, and then our quotient on the right-hand side. So we're left with x squared take away 1. For this example, we are going to use the synthetic method, which I think is by far the easier method. So in order to do that, we are just going to look at the coefficients of the terms here in the polynomial f of x. So we write our terms at the top here, and we're going to leave enough space so we can write underneath. Next, what we need to do is solve for x for our divisor. So our x take away 1, we let that equal 0, and we get x equals 1. So we're going to put that on the left-hand side there. Our very first step is to just bring that 2 down underneath the line, and then we're going to multiply 1 by 2 and write that underneath the negative 4. Next, we're going to add negative 4 and 2. That gives us negative 2. And again, we're going to multiply 1 by negative 2. So we multiply, add, multiply, add. So then we have negative 3 plus negative 2, so we get negative 5. 1 times negative 5 gives us negative 5. And then 6 plus negative 5 gives us 1. So again, we can write our answer like this. We have our dividend and our divisor, and then our quotient on the right-hand side. You can see we have this 1 plus x take away 1. And just noting that the 1 here is the remainder, not this whole fraction. Next, we are looking at factorization of polynomials. This is going to help us sketch higher order polynomials as well. It's also going to help us find what the factors are of our polynomial so we can easily sketch it. So our first step is to substitute a value into the polynomial to find a factor. So we'll have it equaling 0, so it means there's no remainders. The second step is to divide the polynomial by that value to find the other factors. So we have some theorems here which you would have learned last year. So have a look at chapter 3 from unit 1 and 2 methods. For this question, we need to show that x plus 1 is a factor of 2x cubed, take 5x squared, take 4x plus 3, and then we need to find the other linear factors. So firstly, we are going to let x plus 1 equals 0, so we get x equals negative 1, and then substitute that into our polynomial there. Substituting x equals negative 1 gives us negative 2, take away 5, plus 4 plus 3, so we end up getting negative 7 plus 7. equaling 0, so therefore x plus 1 is a factor. Now we are going to use this to divide the polynomial by x plus 1 to find the other linear factors. Using the synthetic method, we get negative 2x squared plus 7x take away 3. And what I've done there is I have rewritten our polynomial in our factored form. So I have x plus 1 and then our quadratic factor on the right-hand side. We then need to factorize the quadratic there so that we have just linear factors. So using the synthetic division, we get negative 2, 7, and negative 3 as our answers. So putting that into quadratic form, we get negative 2x squared plus 7x take away 3, and we're going to let that equal to 0 so we can find the other factors. So I've just multiplied everything by negative 1 to get rid of that negative 2. So we get 2x squared take 7x plus 3. And then I've used the cross method on the right-hand side here to help me find what the other factors are going to be. So doing that, I get 2x take away 1 and then x take away 3 as the other factors. And I've just written them over here. So we have x plus 1, 2x take away 1, and x take away 3 as our factors. So in summary, when we divide f of x by g of x, we get f of x equals the divisor there times by our quotient and then adding our remainder. We have our factor theorem, so these are going to help us find what a factor is. So if we have p of a equaling 0, then x take away a is a factor. And likewise, if we have ax plus b being a factor of p of x, then substituting in negative b on a into p, we get 0. In our next lesson, we are looking at applications of polynomials, so putting together what we have learned and putting them into practice. So we'll see you then. Okay, I do have to apologise. We do try our best to prepare for the exams, and it may seem like this in class. However, what we'll be doing today is putting what we have learned into practice so that you can master those exams. So as I said, in this lesson, we are looking at applications of polynomials. Firstly, we'll be looking at solutions of the form f of x equals g of x, and then we will be modelling polynomials. So when we are solving polynomials in the form of f of x equals g of x, we are looking for where they cross over. The steps to solve for when these cross over is firstly, collect all of the like terms on the left-hand side. So the right-hand side equals 0. Then we're going to substitute values into the equation to find a factor. So what we learned in our previous lesson. Once we have found a factor, we are going to divide the polynomial by this to find the other linear factors. And then we are going to let each factor individually equal 0 to solve for x. So where they are going to intersect. Okay, putting this into practice, so we have the polynomial p of x equals x cubed take away 6x squared plus 7x take away 4, and it says it crosses the line f of x equals 2x take away 4. So we want to find these values where they cross over, so we're letting p of x equal f of x. So firstly, we let p of x equal f of x, so that is what I've done on the first line here. On the second line, I have taken away 2x and then added 4. So that I have all of my terms on the left-hand side. So I've left the right-hand side equal 0. Next, I have collected those like terms. So I have taken away 2x from 7x. So I've added 4 to negative 4, which obviously cancels out to 0. So we end up getting x cubed, take away 6x squared, plus 5x equals 0. What we can do now is take out x as a common factor, leaving us with x times x squared, take 6x plus 5 equals 0. And then we need to find the other factors. So we're going to factorize this here. So our next step is to factorize the x squared take away 6x plus 5. And in doing so, we get x take away 5 times x take away 1. So there are our factors. What we need to do now is let each of these individually equal 0. So we get x equals 0. We get x take away 5 equals 0 and x take away 1 equals 0. And then we need to solve for x. So in doing that, we get x equals 5 and x equals 1 as our other solutions. So for modelling polynomials, we can use them to model different situations to solve problems. Some equations will be given to you, but some you will need to know yourself. So for example, the area and volume formulas, generally they'll be given to you on the exam formula sheet. And when we are modelling using polynomials, it is important to consider appropriate domains within the context of the model. So that's what I've done on the right-hand side there. Just some considerations when specifying a domain. First thing you need to look at is when does a polynomial function exist? So what does it make sense for? So for example, if you are modelling time, it doesn't make sense for our domain to extend to the negative x-axis because we can't really have negative time. If we are modelling volume or area, we need to make sure that our graph does not exceed the parameters of quadrant 1 so that x and y are positive. So that means our area and our volume should be positive. Likewise, if we are modeling volume of items, we need to make sure that our dimensions are greater than 0. If it equals 0, we're not actually going to have any volume there. So again, just be careful. So here's a real life example for you. Ron's actually my dad. He's a farmer. He has a piece of sheet metal with dimensions 90 centimeters by 60 centimeters, and he wants to make an open top toolbox for the back of his ute. So the first question, we need to write an equation for the volume in terms of the height. And secondly, what are the limitations of the height? So firstly, it might be helpful for you to draw a diagram. So that's what I've done on the right-hand side here. I've just drawn a quick rectangle. Don't judge me for my drawings, they're not always great. And I've just made some dotted lines here to show the cutout for the height. So the height is going to be x, and then the side lengths are going to be 90 take away 2x because there's 2 lots of x that you're taking out there. And then the other width is going to be 60 take away 2x because you have 2 lots of x that you are taking away there. So we know our volume is length by width by height. So we have x times 90 take away 2x times 60 take away 2x. Expanding that and simplifying, we get our rule to be 4x cubed take away 300x squared plus 5400x. For B, again, we're looking at the limitations of the height, so how much can we cut out? So let's take into account the smaller side there, the 60 take away 2x. What we're going to do is solve for when this is greater than 0. Again, if it equals 0, there's not going to be any volume there. So we get 60 take away 2x being greater than 0. Adding 2x to both sides, we've got 60 has to be greater than 2x. And then dividing both sides by 2, we get 30 greater than x, or x has to be smaller than 30. So on the left here, we've got x has to be an element of the interval between 0 and 30, so not including either of those. Again, not including 0 because there won't be any height, so therefore no volume. And not including 30 because if it is equal to 30, then again, there's not going to be any width. So the main thing to take away from this lesson is that when you are modeling polynomials and sketching their graphs, make sure you have set an appropriate domain given the context of the model, otherwise it won't make sense. So in the next lesson, we're going to test our skills with the chapter check, which is going to be tech-free.